Good morning everyone. Welcome to the course Stability Aspects of Structural Steel Design, Concepts and Applications. In this class, we can talk about development of width to thickness ratio limits. So far, we have discussed when a member is subjected to axial compression, if you look at it, the cross section is subjected to a uniform compressive stress that is acting across the entire gross area. The column undergoes global buckling. There are three types of global buckling. It is flexural buckling, the second one is torsional buckling, and then the third one is flexural torsional buckling, depending upon the cross-section shape and how the shear center and the centroid coincides. For members that are subjected to transverse loads such as beams, in this case where M0 is the equal moments that are acting on either sides, when we cut the cross-section, we have a compressive force which is linearly varying, that is acting at the top half of the cross-section, and then there is a tensile stress which is linearly varying, that is acting at the bottom half of the cross section. In such scenarios, the beams undergo global buckling. There are two types of global buckling. One is lateral buckling, the another is lateral torsional buckling. Whereas members can also buckle locally, as you can see there is a local buckling that takes place at the elements of the cross section. And structural steel sections consist of plate elements such as flanges, web and stiffeners. They undergo compression, and the elements with high plate slenderness ratios, that is the width to thickness ratios or the depth to thickness ratios. The width to thickness ratios correspond to the flanges and the depth to thickness ratio correspond to the web. When both of them are very high, the plate becomes unstable and buckles locally as shown in the figure on the right hand side. This phenomenon is known as local buckling, and we have obtained the critical stress for plates in our previous sessions. A closer view of the plate buckling is shown on the right hand side, where you can see very clearly the half sine wave buckling that is taking place. The one that is acting at the flanges are simply supported on three sides and free on the other side, and then one that is acting at the web where all four sides are simply supported. And for all four sides simply supported, subjected to uniform axial compression, the generic equation for a critical stress for plates is given as sigma critical equal to K into pi square E divided by 12 into 1 minus nu square into B by T the whole square. Here, K is the elastic plate buckling coefficient, which is a function of boundary conditions, loading conditions as well as aspect ratio. Recall the same thing for columns, where columns, the effective length factor K is a function of boundary conditions only. You should remember that both of them have the factor K. The small factor K is actually representing the plates, and the bigger capital K represents the effective length factor for the columns. Now, let us look at when does local buckling begin. So, local buckling begins in members depending upon the moment curvature relationship as a result of the B by T limits. What you see on the picture is basically the non-dimensionalized moment shown on the y-axis and the non-dimensionalized curvature that is shown on the x-axis. And depending upon the B by T ratios, you can either have compact section, which is class 1, and then you can have class 2 section, and we can have class 3 section. Both of them belong here as non-compact, and then we can also have class 4, which is slender sections. It all depends upon the width to thickness ratios of the cross sections that we take into consideration. So, type 1 is basically class 1, and the moment is given as plastic, and it can achieve plastic hinge rotation, yes. For class 2, it attains the plastic moment and plastic hinge rotation does not take place. Basically, it satisfies the strength criteria, but it does not satisfy the deformation criteria, hence no plastic hinge formation in class 2. The next is class 3, which is the moment reaches the yield moment m sub y and no plastic hinge rotation takes place. The fourth one is class 4, where it reaches the critical buckling stress and hence there is no plastic hinge formation that takes place. This is the work that is carried out by Wilkinson and Hancock, Professor Hancock from University of Sydney, Australia, and this is the research report that is given at the website. And class 4 sections have high plate slenderness ratios, basically B by T or D by T of the cross section elements, compared to class 1, 2 and 3, and class 1, 2 and 3 sections reached yield capacity, while class 4 sections have undergone premature failing due to local buckling. Now, the big takeaway here is that when B by T or D by T, which is the flange slenderness ratios or the web slenderness ratios, increases, local buckling also increases. Now, let us look at class 4 cross sections in design codes. So, the design codes classify the cross sections as class 1, class 2, class 3 and class 4. You can see the picture on the right side where IS 800 shows the same classification for class 1, class 2, class 3, class 4, similar to Euro codes. Let us talk about the width to thickness ratios in design codes. You can see for Euro codes, the table 5.2 gives the width to thickness ratios, whereas table 2 of IS 800 gives you the width to thickness ratios, as you can see here for class 1, class 2 and class 3. Class 4 is not dealt in IS 800, it is dealt in a separate code called IS 801, which is for design of cold form steel. Is there a rationale behind the width to thickness limits in design codes? Is the question, and yes, there is a rationale behind these design codes. But one thing that we need to understand is that the table given in Eurocode is based on yield stress of 235, which is the base yield stress that they have taken into consideration in the development of the codal provisions. As you can see here, the epsilon is given as root of 235 by f sub y, whereas in IS 800, the base value of yield stress is taken as 250 and hence epsilon is given as root of 250 by f sub y. Now, let us look at the rationale behind the width to thickness limits in design codes. The objective here is one is the strength objective, which is to ensure that local buckling does not occur before the cross section develops its full plastic moment capacity, and ensure that the local buckling does not occur before the cross section initiates yielding. The deformation objective is ensure a minimum rotation capacity for the section so that some form of redistribution can occur or energy dissipation can take place. So, the structural steel specifications worldwide use B by T or D by T, which is the flange width to thickness ratios or the web depth to thickness ratios as limits to provide engineers guidance on the impact of local buckling on their designs. How do they do so? Let us look at it. We know the generic equation for elastic critical buckling stress is given as sigma critical, also F critical is given as K into pi square E divided by 12 into 1 minus nu square B by T the whole square, where K is the elastic plate buckling coefficient, E is the Young's modulus, mu is the Poisson's ratio and B by T is the width to thickness ratio of the plate. Now, let us apply square root on both sides. We have root of sigma critical equal to root of K into pi square E divided by 12 into 1 minus mu square, and then outside the root we have 1 by B by T. Now, if the material ceases to be linear elastic at the yield stress sigma y, the above result is valid for sigma critical is equal to sigma y. Now, let us substitute sigma y in place of sigma critical at the onset of yielding. So, we have sigma y equal to root of K into pi square E divided by 12 into 1 minus mu square into 1 by B by T. So, now let us divide with root of 250 on both sides, because we are taking the yield stress base value as 250. We get the value root of sigma y divided by root of 250 is equal to 1 by root of 250 into root of K into pi square E divided by 12 into 1 minus mu square into B by T. Now, B by T is given as 1 by root of 250 into root of K into pi square E divided by 12 into 1 minus mu square into root of 250 by sigma y. Now, substituting E equal to 2 into 10 power 5 Newton per millimeter square and mu equal to 0.3, we get the value of B by T equal to 26.89 into root of K into root of 250 by sigma y. Now, K is the elastic plate buckling coefficient, and what is the value that needs to be considered in the design is a big question. Now, upon substituting the values of K for different boundary conditions, we have for a plate simply supported on all 4 edges subjected to uniform axial compression, we have the value of K equal to 4.0, which we have derived from the previous sessions. We have B by T equal to 53.78 into root of 250 by sigma y. Similarly, when all 3 sides are simply supported and one side is free, we have K equal to 0.425. Hence, when we substitute the value of K equal to 0.425, we have B by T equal to 17.53 into root of 250 by sigma y. Now, when we look at a plate that is simply supported on all 4 edges subjected to pure bending, we have the value of K equal to 23.9. When we substitute the value of K equal to 23.9, we have B by T equal to 131.46 into root of 250 by sigma y. Similarly, a plate simply supported with in-plane shear loading, we have K equal to 5.35. So, the D by T equal to 62.19 into root of 250 by sigma y. Note, The smaller values of B by T or D by T have to be used in the design methods to avoid local buckling of plate elements in steel sections, which is obvious. So, the slenderness of the plate should be as small as possible in order to avoid local buckling, because when you have a higher B by T or D by T ratios, the elements tend to buckle locally, and hence it is important that we have a smaller value of B by T or D by T. The next is the limit B by T or D by T are applicable for perfectly flat plates and do not account for residual stresses and various imperfections which lower the proportional limit, which is very true, because the values of K that we are inputting here is based on a plate that is flat and does not have residual stresses or any other type of imperfections. Third one is that since there can be considerable variations in outer flatness, residual stresses, etc., it is not easy to determine the values to be used in design, and a typical observation from experiments may be that an element with sigma critical to 2 sigma y. So, an element has to be subjected to a stress value ranging between sigma critical to twice the sigma y is needed to develop first yield in a full section. Hence, the design code suggests the limiting value based on judgment. The theoretical elastic buckling stress for a plate is given as sigma critical equal to K into pi square E divided by 12 into 1 minus mu square into B by T the whole square. And if sigma critical by sigma y is defined as 1 by lambda sub c square, the above equation becomes lambda sub c equal to B by T into root of sigma y into 12 into 1 minus mu square divided by pi square E into K. Now, look at the picture on the right hand side. The source is from Heiger and Turliman, the research carried out in 1958, and it has been published in Journal of Engineering Mechanics Division, AISCE. You can see that there is a non-dimensionalized stress that is shown in the y-axis, and then you have a non-dimensionalized slenderness that is shown on the x-axis, and you have three different curves, the one curve for the column and another curve for the plate that is supported on three sides and one side is free, and then there is another curve C which is for a plate that is all four sides simply supported. So, from the figure, the plates curve B and C achieve the strain hardening condition at values of lambda relatively higher than those of the columns, which is obvious from the picture that you can see here. And the value of lambda sub C at which strain hardening commences is denoted by lambda naught. So, the lambda naught for a column is 0.17, for a plate that is simply supported on all three sides and one side is free is given as 0.46, and a plate that is supported on all four edges is given as 0.58. For plates without residual stresses, three regions must be considered for establishing the strength. The region 1 is the elastic buckling region, which is the Euler hyperbola given as 1 by lambda sub c square. The next is the yielding segments, which is segments AB, A dash B and A double dash B, and the third one is the strain hardening segment that is seen here. So, points A dash and A double dash represents points where the inelastic buckling curve ends and the strain hardening curve begins, as you can see on the picture as is shown here. So, the one that goes up is the strain hardening portion, and the one that is shown here between A and B and A dash and B and A double dash and B corresponds to the inelastic buckling that takes place in column and the inelastic buckling that takes place in plate, all three sides simply supported, one side free, and the inelastic buckling that takes place between the plates that are supported on all four edges, that is A double dash to B. So, A for columns, A dash for plates supported along one edge and A double dash for plates supported along two edges. Now, Heiger and Turliman determined lambda naught for the 5 cases given in the table, as you can see here. So, the non-dimensionalized slenderness curve for initiation of strain hardening is given as for columns 0.173, and for hinged flanges it is given as 0.455, for fixed flanges it is given as 0.461, and for hinged webs it is 0.588 and fixed webs it is given as 0.579. So, for columns it is curve A, and for hinged flanges and fixed flanges it is curve B, and curve C for hinged webs and fixed webs. To make life simple, they took an average value for curve B and which is given as 0.46, and curve C it is given as 0.58. So, from the data it is apparent that the important factor in determining lambda naught is whether the plate is supported along one edge or two edges, and the degree of edge restraint hinged or fixed essentially has no effect. So, for one edge simply supported, the unstiffened elements lambda naught can be taken as 0.46, as you can see here highlighted, and then for both edges supported, the stiffened elements lambda naught can be taken as 0.58, also highlighted on the right side of the curve, and these values are shown in the plot. Now, let us look at the comparison of width to thickness limits in AISC 360 with IS 800 2007. For a beam to attain the plastic moment without buckling, the width to thickness ratio B by T must not exceed lambda sub naught. So, lambda sub C is given as B by T into root of sigma y into 12 into 1 minus mu square divided by pi square E into K, which we have derived in the previous slides. And so, we have to ensure that the B by T must not exceed lambda naught. So, we substitute lambda sub C equal to lambda naught and rearrange the equation in terms of B by T. So, B by T should be less than or equal to lambda naught into root of pi square E into K divided by sigma y into 12 into 1 minus 0.3 the whole square. When we run the numbers, we get 0.95 lambda naught into root of K into E divided by sigma y. Now, for unstiffened elements, we know that lambda naught is equal to 0.46 from the previous plot based on the work carried out by Turliman. So, we have the B by T equal to 0.95 into 0.46 into root of K into E divided by sigma y, which becomes 0.437 into root of K E divided by sigma y. And for stiffened elements, it becomes B by T equal to 0.95 into the lambda naught here is 0.58 into root of K E divided by sigma y, which becomes 0.551 into root of K E divided by sigma y. Now, for example, let us consider the flanges of I-shaped sections under bending. Now, for the flange of an I shape, the web will provide the restraint somewhere between fixed condition where K can be 1.277 and simple condition where K can be 0.425, and the theoretical buckling coefficients are shown on the right hand side depending upon the edge support. Here we are assuming that the loaded edges are almost always simply supported, and the edge support conditions that are shown here is only for the unloaded edges. So, when the unloaded edges are simple, we have K equal to 4.0. When the unloaded edges are fixed and simple, K is 5.42. When the unloaded edges are fixed and fixed, K is 6.97. When the unloaded edges are fixed and free, K is 1.277. And when the unloaded edges are simple and free, K is 0.425. All these things are theoretically derived based on energy approach that we have previously seen in previous classes. Now, here we are focused only on fixed free conditions as well as simple free conditions. The value ranges between 0.425 to 1.277. Hence, the value of K is taken as 0.7, which is basically lies midway between simply supported and fixed conditions. When we substitute 0.7, we have B by T equal to 0.437 into root of 0.7 into E divided by Fy, which gives the value of 0.37 into root of E by Fy. This is very similar to the value given in AISC 360 for flanges of rolled I sections under flexure, which is 0.38 into root of E by Fy. You can also see from table B4.1b, you can see that highlighted portions lambda sub B equal to 0.38 into root of E by F sub Y. Now, when we substitute this one, E equal to 2 into 10 power 5, and we also multiply and divide by 250 to introduce the strain limit epsilon, we have 10.7 into root of 250 by Fy, which is nothing but 10.5 into epsilon, which is the limit for compact sections stipulated by IS 800 2007 for outstanding elements of rolled I shapes, which is shown on the right hand side of the picture. Table 2, you can see that class 2 compact, you have 10.5 as the limiting value. Now, how about for semi-compact sections in IS 800 2007, which is 15.7 epsilon? Now, we can go to AISC, which gives B by T equal to 0.56 into root of E by F sub Y for flanges of rolled steel sections under compression. And when we substitute the values here, we get 15.8 into root of 250 by Fy, which is very similar to 15.7 epsilon given in IS 800. So, you can see that the limiting value is 15.7 for class 3 semi-compact for outstanding elements of rolled I shapes. So, the point to remember here is that a conservative approach is taken for achieving limiting B by T for outstanding element of compression flange in IS 800 based on either uniform compression or flexure. For flanges of box section under bending, assuming that the webs provide little rotational support to the flange, the elastic plate buckling coefficient K equal to 4.0 can be taken from the case of plate with all sides simply supported. So, for stiffened elements, the B by T ratio is given as 0.551 into root of 4 into E by F sub Y, which comes to 1.1 into root of E by f sub y. So, which is very similar to 1.12 into root of E by f sub y given in AISC 360 for flanges of a box section under flexure. You can see that the right hand side, the table B 4.1, which is given row number 21 for flanges of box sections highlighted as 1.12 into root of E by f sub y. How about IS 800 2007? Now, IS 800 2007 is not very conservative, so it takes an average between the simple support conditions as well as fixed support conditions. K value is ranging from 4 and 6.97, and average value is very close to 5.485. So, when we substitute 5.485 in the above equation, we get a value of 36.49 into root of 250 by Fy. Now, this is very close to 33.5 epsilon. So, even in average, we are not very close to the fixed condition, we are keeping it very lower than the fixed condition. So, it is midway between a simply supported condition and average of simple support and fixed conditions, because the value is now reduced again from 36.49 and our value given in IS 800 is 33.5 epsilon. So, this is the limit for compact sections stipulated by IS 800 2007 for internal element of compression flange. As you can see here, it is given as 33.5 in table 2 under class 2 compact for internal element of compression flange. Now, let us look at AISC 360, which is given as B by T equal to 1.49 into root of E by f sub y flanges of box sections under flexure, which is under non-compact condition. So, when we substitute these values, we get 42.1 into root of 250 by f sub y, which is the strain limit of 42 epsilon, that is given in IS 800. So, the limit for semi-compact section stipulated by IS 800 2007 for internal element of compression flange is given as 42 epsilon, as you can see on the picture on the right hand side, which is class 3 semi-compact. With this one, we complete the discussion on slenderness ratios for plates, and we will come up with more such discussions on plated structures in the next class. Thank you very much.